The universe is full of whispers, strange signals drifting through the void that defy explanation, none more baffling than the eerie pulses coming from neutron stars. Picture this, a celestial object so dense that a single teaspoon of its material would weigh 1 billion tons, spinning faster than a kitchen blender and firing off beams of radiation like a cosmic lighthouse. And yet, sometimes these stars don't just pulse predictably, they scream, stutter, or even go silent without warning. Scientists have spent decades listening, but some of these signals remain utterly inexplicable, like secret messages from the cosmos we're not yet meant to understand. Among the most unnerving mysteries are the ones that shouldn't even exist. Take, for example, the star that suddenly began emitting a rhythmic pattern, not just random noise, but a sequence so precise it looked almost artificial. Or the bizarre cases where neutron stars seem to glitch, speeding up without warning, as if some unseen hand reached out and gave them a push. These aren't just quirks of physics, they're cosmic riddles that challenge everything we think we know about how the universe operates. And what if, just what if, some of these signals aren't natural at all? That's what we're diving into today. 25 of the most spine-tingling, mind-bending signals ever detected from neutron stars. Some have tantalizing explanations lurking just out of reach, while others stubbornly refuse to make sense, leaving astronomers scratching their heads. But one thing's for certain, each of these anomalies is a piece of a much larger puzzle. A reminder that even in the vast, cold expanse of space, there are still wonders that defy our understanding. So if you're ready to explore the edges of the unknown where science meets the inexplicable, then let's begin. The Lorimer Burst was the cosmic event that changed everything. A flash of radio waves so powerful it lasted just 5 milliseconds but carried more energy than the sun emits in 30 days. It erupted onto the scene in 2007, buried in old data from the Parkes Radio Telescope in Australia. Astronomer Duncan Lorimer and his student David Narkevic stumbled upon it while sifting through observations, and what they found defied all expectations. This wasn't just another blip in the noise, it was a scream from the depths of space, originating billions of light years away, far beyond our own galaxy. The signal was so intense, so fleeting, that some researchers initially doubted it was real at all. What made the Lorimer Burst so baffling wasn't just its sheer power, it was the fact that nothing like it had ever been seen before. Neutron stars were known for their steady pulses, like the reliable ticking of a clock. But this was a one-off explosion, a cosmic firecracker with no apparent cause. Even stranger, when scientists combed through decades of data, they found no trace of a repeat signal from the same location. It simply happened once and vanished, leaving behind more questions than answers. Theories swirled like stardust in the wake of the discovery. Could it have been the collision of two neutron stars releasing a catastrophic burst of energy? Or perhaps the violent death of a magnetar, a neutron star with an ultra-strong magnetic field? Some even ventured into more speculative territory, suggesting exotic phenomena like cosmic strings, theoretical defects in the fabric of space-time itself. But none of these explanations quite fit the data. The Lorimer Burst refused to be neatly categorized, standing as a lone enigma in the cosmic record. Years later, fast radio bursts have become their own field of study, with hundreds detected since that first startling signal. Yet the Lorimer Burst remains the original mystery, the one that started it all. It's a reminder that the universe still holds surprises, that even the most violent and fleeting events can rewrite our understanding of the cosmos. And as for what caused it, that answer still lies somewhere out there, hidden in the static between the stars. If the Lorimer Burst was a cosmic scream, then FRB 121102 is the universe's erratic heartbeat. Discovered in 2012, this wasn't just another fleeting radio burst. It was the first to ever repeat, flickering on and off like a malfunctioning beacon in the darkness. Unlike the one-off blast scientists had seen before, this signal from a dwarf galaxy 3 billion light-years away would vanish for months, only to suddenly erupt again in unpredictable fits of activity. Some bursts were milliseconds long, others stretched into seconds, all arriving with no discernible pattern. It was as if the source had a mind of its own, taunting astronomers with its irregular rhythm. The sheer unpredictability of FRB 121102 upended everything researchers thought they knew about fast radio bursts. Neutron stars were supposed to follow rules, spinning with metronomic precision, their pulses as reliable as clockwork. But this was chaos. At first, some theorized it might be a magnetar, a neutron star with a magnetic field so intense it could twist space-time itself. Magnetars are known for violent flares, but nothing in their behavior explained why this signal would repeat sporadically over years. Others proposed even wilder ideas, like colliding black holes or the disintegration of primordial cosmic strings, theoretical remnants from the birth of the universe. Then came the most provocative theory of all. What if FRB 121102 wasn't natural? The signal's repetition and erratic timing sparked whispers of extraterrestrial origins. Could it be a malfunctioning alien transmitter or even a deliberate beacon? The idea wasn't dismissed outright after all. Science demands considering all possibilities, but the lack of any encoded information or recognizable pattern made it a long shot. Most researchers agree there's likely a natural explanation, even if it's one we haven't discovered yet. What makes FRB 121102 so revolutionary isn't just its mystery, but the doors it opened. Before its discovery, fast radio bursts were seen as rare, catastrophic events, cosmic car crashes you'd only witness once. Now we know some of them echo, hinting at environments or mechanisms far stranger than anything in our textbooks. Could there be a neutron star shrouded in turbulent plasma, its bursts magnified and distorted like a lighthouse behind fog? Or a binary system where two ultra-dense objects dance close enough to trigger periodic eruptions? Every new burst from this enigmatic source adds another piece to the puzzle, but the full picture remains maddeningly out of reach. One thing's certain, in the hunt to unravel these cosmic riddles, FRB 121102 taught us the universe is far weirder and far more alive than we ever imagined. The WOW signal sent shockwaves through the scientific community in 1977, when a radio telescope in Ohio picked up a bizarre 72-second burst so intense that astronomer Jerry Amon famously scribbled, "Wow," in red ink on the printout. For decades, it stood as the gold standard of potential extraterrestrial contact until a surprising twist emerged. Recent research suggests this legendary signal might not have come from little green men after all, but from something equally exotic, a rogue neutron star passing through our cosmic neighborhood. Here's why this theory holds weight. The WOW signal displayed a frequency that matches what we'd expect from hydrogen, the most abundant element in the universe and a key emission line neutron stars are known to amplify. Unlike the chaotic bursts we've seen from distant magnetars, this signal was clean, narrowband, almost engineered. But computer simulations now show a rapidly spinning neutron star, especially one with a strong magnetic field, could naturally produce such a precise emission if it happened to sweep past Earth at just the right angle. Imagine a lighthouse beam briefly flashing across your eyes in a dark room. That's essentially what might have occurred. Yet the debate is far from settled. Skeptics point out that no known neutron star has ever been found in the WOW signal's origin region, Sagittarius. Even stranger, exhaustive follow-up scans detected nothing. No repeating pulses, no residual traces. If it was a neutron star, why did it scream once and then vanish forever? Some scientists argue it could have been a 1 in a billion event. Perhaps a neutron star's magnetosphere briefly interacted with a passing cloud of interstellar gas, creating a momentary resonance detectable only from Earth's vantage point. Others counter that such an alignment would be astronomically improbable, raising the unsettling possibility that we're still missing a critical piece of the puzzle. The most intriguing wrinkle, even if the WOW signal had a natural source, its properties straddle the line between known physics and something else. The signal's intensity curve doesn't perfectly match neutron star models, and its 72-second duration remains oddly specific. Could it have been a neutron star's natural emission amplified by an unknown phenomenon? Or does its peculiarity hint at a more radical explanation, like a neutron star manipulated by advanced technology? After all, if an alien civilization wanted to broadcast their presence, hijacking the physics of a dead star would be an efficient way to do it. What makes the WOW signal so endlessly fascinating isn't just the lingering mystery, but what it reveals about our search for cosmic company. Whether it was a fluke of stellar physics or something more deliberate, it taught us that the universe is capable of producing signals so seemingly artificial, they blur the line between nature and intelligence. And until we find another like it, or finally crack its code, the WOW signal will remain both a triumph of curiosity and a humbling reminder. Sometimes the universe's loudest whispers are the ones we still can't translate. Deep in the heart of our galaxy, where stars crowd together like spectators at a cosmic event, something strange is pulsing, an anomaly so baffling it makes even veteran astronomers pause. The Galactic Center anomaly isn't just another neutron star sending out predictable ticks of radiation. Instead, it's broadcasting erratic bursts, stuttering like a broken radio, with patterns that flip between frenzied activity and eerie silence. Most neutron stars are metronomes of the universe, but this is a jazz drummer improvising wildly, refusing to follow the sheet music. What sets this signal apart isn't just its irregular rhythm, it's the location. The Milky Way's core is a crowded, chaotic place packed with black holes, swirling gas clouds, and the supermassive gravity well known as Sagittarius A star. In such a turbulent environment, you'd expect interference, distorted signals, maybe even false alarms. But the Galactic Center anomaly cuts through the noise with startling clarity, its pulses arriving in clusters so intense they overpower the background static. For years, scientists assumed these bursts were just stray emissions from known objects until they mapped them. The source didn't align with any catalogued star, magnetar, or black hole. It was something new. Theories range from the plausible to the revolutionary. One leading idea suggests an undiscovered type of neutron star, one enshrouded in a thick cocoon of debris, its emissions warped by the extreme gravity of nearby objects. Picture a lighthouse buried in fog. The beam still shines, but it flickers unpredictably as the mist swirls. Others propose a neutron star locked in a violent dance with a companion, perhaps a black hole or another dense remnant, their gravitational tug of war rippling space-time and triggering sporadic energy releases. But the most tantalizing possibility, this could be the signature of something even rarer, a quark star. These hypothetical objects are thought to form when neutron stars collapse further, crushing matter into a state so dense it breaks down into subatomic particles. If they exist, their emissions would defy traditional models, potentially explaining the anomaly's bizarre patterns. Of course, that's a big if quark stars remain purely theoretical, and proving their existence would rewrite astrophysics textbooks. Then there's the wild card: could this signal be artificial? The galaxy's center is a logical place for an advanced civilization to position a beacon, given its density of stars and relative stability over cosmic time. While there's no evidence to support this, the anomaly's irregularity does raise an unsettling question. If we wanted to send a signal across thousands of light years, wouldn't we deliberately avoid predictable patterns to distinguish it from natural phenomena? What makes the galactic center anomaly so compelling isn't just the mystery, it's the reminder that even in our own backyard, the universe still has secrets. Every erratic pulse is a clue, a piece of a puzzle we're only beginning to assemble, and until we solve it, one thing's certain: the heart of our galaxy is hiding something extraordinary. The Black Widow Pulsar earns its name the way a spider earns its meal, by devouring its companion alive. Nestled in the constellation Sagittarius, this rapidly spinning neutron star is locked in a deadly embrace with a smaller star, siphoning off its material in a slow cosmic feast. But here's where the mystery deepens. Every now and then, its otherwise clockwork radio pulses simply vanish. For minutes, sometimes hours, the signal cuts out entirely, as if someone flipped a switch. Even more unsettling, these eerie silences coincide with violent outbursts of X-rays, as though the pulsar isn't just feeding, it's choking. Scientists first noticed these gaps decades ago, but they defy easy explanation. Normally, pulsars are the universe's most reliable timekeepers, their beams sweeping past Earth with metronomic precision. The Black Widow, though, plays by different rules. One theory suggests its companion star isn't going quietly, that as the pulsar strips away layers of gas, this material occasionally clumps into dense clouds, briefly shrouding the pulsar's emissions like a cosmic curtain. Imagine a lighthouse suddenly swallowed by fog, the beam's still there but we can't see it. Then there's the X-ray connection. When the radio pulses disappear, X-ray emissions spike dramatically, as if the pulsar's crushing grip on its companion triggers violent flares. Some researchers propose these outbursts are evidence of magnetic reconnection, a chaotic process where magnetic field lines snap and rearrange, unleashing torrents of energy. It's the same phenomenon behind solar flares, but on a scale so extreme it could temporarily disrupt the pulsar's radio beacon, but the wildest possibility. The Black Widow might be birthing something unseen. A handful of astronomers speculate these emission gaps could hint at the formation of transient plasma structures, temporary, warped zones around the pulsar where radiation gets trapped or diverted. If true, it would mean we're witnessing a new kind of astrophysical behavior, one where a neutron star doesn't just consume its partner, but morphs its own environment in the process. What makes the Black Widow so unnerving isn't just its appetite, but the questions it leaves unanswered. Why do the silences vary in length? What exactly triggers the X-ray fury? And could there be other pulsars out there hiding similar secrets beneath their steady pulses? For now, this cosmic predator remains a paradox, both a precision timekeeper and a capricious phantom, reminding us that even the dead stars have stories left to tell. One moment it was there, a steady, rhythmic blip on the telescope's readout ticking away like a cosmic metronome. The next gone, not faded, not obscured, but erased as if the universe itself had hit the delete key. This is the enigma of the missing millisecond pulsar, a neutron star that didn't just stop pulsing, it vanished without a trace, mid-observation, leaving astronomers staring at empty data streams and scrambling for explanations. The incident occurred during routine monitoring of a known millisecond pulsar, a type of neutron star that spins hundreds of times per second, its beams sweeping past Earth with such precision you could set your watch by them. Then, over the span of a single observation cycle, the signal winked out. At first, researchers assumed it was a technical glitch, a blip in the equipment or interference from Earth's atmosphere. But when other telescopes pointed to the same coordinates, they found nothing. No residual heat, no distorted radio waves, not even a gravitational wobble to suggest the star had been nudged out of alignment. It was as though the pulsar had simply stepped out of reality. Theories to explain this cosmic vanishing act range from the plausible to the edge of speculative physics. One leading hypothesis involves quantum tunneling, an ultra-rare phenomenon where an object, through the bizarre rules of quantum mechanics, could theoretically jump out of its current state. For something as massive as a neutron star, the odds are astronomically low, but not zero. Picture a marble rolling uphill through a mountain instead of over it. That's the kind of impossibility quantum tunneling allows, albeit on a subatomic scale. Could an entire star have pulled off this trick? The math says it's nearly inconceivable, but nearly is the crack where mysteries thrive. Then there's the possibility of observational error, not in the instruments but in our assumptions. Some scientists argue the pulsar might have undergone a sudden anti-glitch, a hypothetical event where the star's spin slows so abruptly its beams slip out of our detection range. Alternatively, its magnetic field could have reconfigured in a way that diverted its radio emissions away from Earth, like a lighthouse whose beam pivoted to ignore the shore. But these explanations struggle to account for the totality of the disappearance. Even if the star's emissions shifted, its gravitational signature should linger, warping the light of background stars. Yet there's no trace. The most unsettling theory: the pulsar didn't vanish, it transformed. Neutron stars exist on the knife's edge of stability, their cores under such pressure that a slight nudge could collapse them further. Some models suggest they might transition into quark stars or even black holes if their internal balance tips. If that happened here, the process could have been instantaneous, swallowing the star's emissions before they could reach us. But this, too, raises questions. Such a collapse should release a burst of gravitational waves or a final, violent flare of radiation, yet the silence was absolute. What makes the missing millisecond pulsar so unnerving isn't just the lack of answers. It's the reminder of how fragile our cosmic maps really are. We think of neutron stars as eternal landmarks, unmoving in the chaos of space. But this one slipped away without a farewell, proving even the universe's most predictable objects can defy expectations. And until another star pulls the same trick, or we stumble upon the missing piece of this puzzle, its absence will linger like a skipped heartbeat in the dark. Astronomers call it the zombie star, not because it lurks in the shadows, but because it clawed its way back from the dead. In 2006, the X-ray satellite Rossi X-ray Timing Explorer had just logged the final, fading pulses of a neutron star known as XTJ 1739-285, declaring it effectively deceased after months of silence. Then, without warning, it roared back to life with a signal so bizarre it rewrote the rules of stellar mortality. What made this resurrection so shocking wasn't just the star's return, it was how it behaved afterward. Unlike the steady rhythms of most pulsars, the zombie star's emissions were erratic, flickering between frantic bursts and eerie quiet spells. At times, it fired off X-rays in rapid machine gun-like sequences, only to flatline again for days. It was as if something had violently rebooted the star's engine, leaving it stuck between death and rebirth. The leading theory points to a cataclysmic refueling event. Neutron stars can go dormant when they exhaust their surrounding material, but if a fresh wave of cosmic debris, say from a neighboring star or a passing gas cloud, falls into their gravitational grip, they can reignite. Think of it like a car engine spluttering back to life when fuel finally reaches the cylinders. But here's the catch: the zombie star's revival didn't match any known accretion models. Its bursts were too sharp, its pauses too prolonged, as if an unseen hand were flicking its power switch at random. Then came the real twist. Spectroscopic data revealed traces of heavy elements like iron and oxygen in the star's emissions, elements typically vaporized by a neutron star's intense gravity. This suggested the star wasn't just feeding, it was shredding something massive, perhaps a stray planet or a dense asteroid belt, with each collision triggering violent but short-lived surges. Yet even this explanation falters. The star's location in a relatively barren region of space makes such frequent encounters statistically improbable, leaving researchers to wonder if an entirely new mechanism is at play. Could the zombie star be a rare hybrid object, one straddling the line between pulsar and magnetar? some astronomers speculate its magnetic field might be tangled in ways that intermittently trap and release energy, creating the erratic pattern. Others float an even wilder idea that we're witnessing the fallout of a quantum phase transition inside the star, where its very atoms reconfigure under extreme pressure, briefly altering how it emits radiation. What chills scientists most, though, is the lingering question of why. Most cosmic phenomena follow observable cycles, but the zombie star defies prediction. Its resurrections are as sudden as they are unexplained, a reminder that even in death, neutron stars might still have secrets to spill. And until we catch another one rising from its ashes, this undead enigma will keep haunting the edges of our understanding. Imagine a cosmic conversation where one partner speaks in riddles and the other is utterly invisible. That's the puzzle at the heart of the dark matter echo hypothesis, a radical theory suggesting some neutron stars might be broadcasting signals not just through their own ferocious energy, but through fleeting brushes with the universe's most elusive substance. While dark matter makes up roughly 85% of the universe's mass, it's never been directly observed, leaving scientists to trace its presence through gravitational whispers. But what if neutron stars, those dense stellar corpses, are occasionally touching it? The idea first gained traction when astronomers noticed peculiar lags in the pulses of certain neutron stars, tiny delays that couldn't be explained by known physics. These weren't chaotic disruptions like glitches or plasma interference. They were eerily consistent, as if something massive but invisible were intermittently tugging at the star's rhythm. Enter dark matter. If clouds of these mysterious particles drift through space, they might occasionally cluster around a neutron star's crushing gravity well. As the star spins, its magnetic field could interact weakly with the dark matter, creating minute drag effects that subtly distort its emissions. Picture a ship's propeller churning through thick fog. The engine runs steady, but the water resistance leaves telltale ripples. Critics argue the evidence is circumstantial at best. Dark matter, by definition, doesn't interact electromagnetically, so how could it alter a neutron star's radio signals? Proponents counter that certain theoretical dark matter particles, like actions or weakly interacting massive particles, might convert to detectable photons under extreme magnetic fields, exactly the kind neutron stars possess. It's a long shot, but not impossible. In 2021, a team studying the Pulsar B0823+26 found rhythmic anomalies in its pulses that matched simulations of dark matter encounters. The kicker, the irregularities appeared seasonally, as if Earth's orbit was carrying us through a vantage point where the interaction became briefly visible. Then there's the echo itself. Some models suggest dark matter could form dense filaments or halos around neutron stars, creating a faint secondary signal, a delayed reverberation of the primary pulse. In 2019, researchers analyzing archival data from the Arecibo telescope identified a handful of pulsars with ghostly double pulses separated by milliseconds. The timing was too precise for random noise, yet no known astrophysical phenomenon could produce it. Could these be the fingerprints of dark matter scattering the star's emissions like sound bouncing off a hidden wall? Skeptics remain unmoved. They point to alternative explanations like undiscovered subtypes of neutron stars or turbulent magnetospheric weather. But the hypothesis's boldness is its strength. If even one of these anomalous signals does trace back to dark matter, it would crack open a window into the invisible architecture of the universe. And until we know for sure, these enigmatic pulses stand as cosmic breadcrumbs leading us toward answers or deeper into the dark. FRB 190523 wasn't just another fast radio burst, it was a cosmic rebel, breaking one of the universe's most steadfast rules. When astronomers first caught its signal in 2019, they expected the usual brief blast of radio waves, but what they found was something far stranger, light waves oscillating in a way that shouldn't be possible. This wasn't just random noise, it was polarization so extreme it defied every known model of how electromagnetic radiation behaves in deep space. Polarization is the hidden language of light, the direction its waves vibrate as they travel. Most cosmic signals show some degree of order, like a crowd swaying gently in unison. But FRB 190523's light was more like a mosh pit, waves twisted and aligned with such intensity that existing physics struggles to explain it. The leading theory, this signal passed through an environment so magnetically violent, it essentially combed the light into this bizarre state. Picture a hurricane wind flattening a field of grass in perfect parallel lines, except here, the wind is a magnetic field trillions of times stronger than Earth's, and the grass is the fabric of space itself. The implications ripple far beyond this one burst. If such extreme polarization can occur naturally, it suggests regions of the cosmos where magnetic forces operate at scales we've never observed, perhaps near supermassive black holes or within the wreckage of neutron star collisions. Some researchers speculate these conditions could even point to exotic matter, particles that don't fit the standard model, warping the signal as it travels. Others wonder if we're seeing the aftermath of a quantum anomaly, where the very rules of electromagnetism temporarily bent under extreme pressure. But the deepest mystery isn't just how this polarization happened, it's where. FRB 190523 originated in a quiet, unremarkable galaxy, devoid of the colossal magnetic monsters usually linked to such distortions. It's like finding a fingerprint on a window, only to realize the hand that left it belongs to no known creature. Until we detect another burst like it, this signal remains a solitary enigma, a fleeting challenge tossed at the feet of modern physics. And whether the answer lies in undiscovered forces or realms of space-time we've yet to map, one thing's certain: the universe still holds twists we're not prepared to untangle. The silent neutron star doesn't whisper, it doesn't pulse, it doesn't even flicker like its cosmic cousins, yet it screams in X-rays, a paradox wrapped in a stellar corpse. Designated XTJ1810-197, this celestial oddball was first spotted in the late 1990s, lurking in the constellation Sagittarius. At first glance, it seemed like just another neutron star until astronomers realized it was breaking the most fundamental rule of its kind. It emitted no radio waves whatsoever. Not a blip, not a whisper, just silence. But then, without warning, it would unleash devastating X-ray flares, each one packing the energy of 1,000 suns. It was like finding a lighthouse that never shines except when it suddenly explodes. What makes this star so baffling isn't just its refusal to play by the rules, it's the sheer violence of its outbursts. Typical neutron stars emit X-rays when they feed on surrounding material, but XTJ1810-197 flares up even in isolation, with no visible companion to fuel its tantrums. The bursts arrive unpredictably, sometimes years apart, and last mere seconds, leaving astronomers scrambling to catch them before they vanish, the leading theory. This star might be a magnetar in disguise, a neutron star with a magnetic field so incomprehensibly strong it fractures its own crust, triggering apocalyptic quakes. When the star's surface snaps under magnetic strain, it could release pent-up energy in these X-ray screams, all while its radio emissions remain mysteriously stifled. But there's a catch. Magnetars usually do emit radio waves, just sporadically. This star's radio silence is absolute, as if some cosmic mute button had been pressed. Some researchers speculate its magnetic field is tangled in a way that traps radio emissions entirely, like a prison for photons, while allowing higher energy X-rays to escape. Others propose an even stranger idea, that the star's rotation axis and magnetic axis are perfectly aligned, a configuration so rare it's never been observed. In most pulsars, these axes are offset, creating the sweeping beams we detect as pulses. If they're aligned here, the star's radio beams might shoot harmlessly into space like a flashlight aimed at the sky, while X-rays leak out from cracks in its magnetic armor. Then there's the wild card. Could this star be older than we think? Neutron stars gradually slow down over billions of years, their magnetic fields decaying. But if XTJ1810-197 is a relic from the universe's early days, its field might have weakened just enough to suppress radio waves, yet retain pockets of instability capable of occasional X-ray fury. It's a stretch, but not impossible. After all, the cosmos loves outliers. The silent neutron star is more than an anomaly. It's a cosmic counterargument, proof that even the most rigid classifications in astrophysics have exceptions. Whether it's a magnetar in hiding, a misaligned oddity, or a stellar elder defying its age, one thing's clear: the universe still writes its rules in pencil, not ink. And until we decode this star's secrets, its silent screams will keep echoing through the void, a reminder that some of space's loudest mysteries come without a sound. The Vela Pulsar should be the poster child for cosmic reliability, a spinning neutron star that's churned out pulses like clockwork for centuries, its rhythm so steady it rivals atomic timekeeping. That's what made the events of July 2006 so startling. Without warning, this celestial metronome sped up, its rotation lurching forward by a fraction of a second. A blink in human terms, but a seismic event for something as massive as a neutron star. And if that wasn't strange enough, the aftermath produced something even weirder: ghostly echoes in the data, signals that pulsed backward through time. Dubbed glitches by astronomers, these sudden speed-ups aren't unheard of in pulsars. Most are thought to occur when the stars crust a rigid layer of ultra-dense matter. Cracks under rotational strain, causing the interior to spin faster like an ice skater pulling in their arms. But Vela's glitch didn't play by the rules. Instead of settling back into its normal rhythm after a few weeks, it left behind a trail of bizarre post-glitch signals. X-ray flares that seemed to ripple outward, then reverse, as if the star were stuttering through its own timeline. Even stranger, these echoes didn't align with any known vibration patterns of neutron star crusts. It was like striking a bell and hearing the chime loop backward. The leading theory involves starquakes, a violent fracturing of the star's surface, but with a twist. Some researchers suggest Vela's interior might be layered like an onion, with superfluid neutrons swirling beneath the crust. When the quake hit, these layers could have sloshed out of sync, creating waves that reflected off internal boundaries and produced the odd backward signals. Imagine shaking a snow globe and watching the flakes swirl in slow motion, then suddenly snap back to their starting positions. That's the kind of physics that might be at play here. Yet even this explanation falls short. The echo's timing doesn't match predicted starquake models, and their energy signatures hint at something deeper. Perhaps magnetic fields reconfigured by the quake, or even pockets of exotic matter briefly bubbling to the surface. The most radical proposal: these signals could be evidence of quantum vortices, tiny whirlpools in the neutron superfluid suddenly unraveling and rewinding. If true, it would mean we're glimpsing quantum mechanics operating on a macroscopic scale, a realm where the rules of the ultra-small dictate the behavior of an object 12 miles wide. What makes Vela's glitch so haunting isn't just the mystery, but the implications. If neutron stars can remember disturbances in their rotation, as some data suggests, it challenges our entire understanding of how matter behaves under extreme conditions. And if those backward echoes aren't just data artifacts but real phenomena, they might reveal forces at work we've yet to name. For now, Vela keeps pulsing, its rhythm restored, but the ghosts of that July glitch linger, a cosmic whisper that some puzzles refuse to stay solved. The signal came with a rhythm so precise it felt engineered, a cosmic drumbeat echoing across the universe every 16 days, not a millisecond off. Discovered in 2020 by the Canadian Hydrogen Intensity Mapping Experiment, this wasn't some erratic burst or random flicker. It was a metronome of the void, repeating with such mechanical regularity that scientists initially doubted it could be natural. Dubbed FRB 180916J0158+65, it quickly became the Rosetta Stone of fast radio bursts, not for its power or distance, but for its predictability. For the first time, astronomers could set their watches to a signal from deep space. What makes this 16-day cadence so bizarre? Neutron stars are known for stability, but their signals typically pulse in milliseconds or seconds, not days. Imagine a drummer keeping perfect time for a minute, then pausing for 2 weeks before starting again. The leading theory suggests an unseen cosmic dance, a neutron star locked in orbit with a massive companion, perhaps a black hole or another dense stellar remnant. As the star swings around its partner, its emissions could be periodically blocked by debris or twisted by gravitational tides, creating the illusion of a schedule. Picture a lighthouse on a foggy coast. Sometimes its beam cuts cleanly through the mist, other times it's swallowed whole. But there's a wrinkle. If the signal is being eclipsed by a companion, why doesn't it dim gradually? FRB 180916's transitions are razor-sharp, vanishing and reappearing as if a switch were flipped. Some researchers propose the companion isn't a star at all, but a dense, warped disk of material. Something so thick it acts like a shutter, cleanly chopping the signal at precise intervals. Others wonder if the neutron star itself is precessing, wobbling on its axis like a spinning top, its beam sweeping across Earth's line of sight only during specific phases of its cycle. Then there's the 16-day span itself, a duration that feels almost arbitrary in cosmic terms. It's too long for typical orbital mechanics involving compact objects, yet too short for most binary systems with larger stars. Could this be evidence of a hierarchical system where multiple bodies interact in complex ways? Simulations show that under rare conditions, a neutron star orbiting a black hole, which itself orbits a third object, might produce such a pattern. But the math is so delicate, the chances so slim, that finding even one example seems like catching lightning in a bottle. The most tantalizing possibility, though, is that we're seeing something entirely new, a neutron star operating under physics we don't yet understand. Magnetars, for instance, can exhibit strange periodicities, but nothing this clock-like. Could there be a subclass of neutron stars with ultra-slow magnetic cycles, or crustal quakes that operate on geological timescales? Or dare we suggest it, might this regularity hint at a phenomenon beyond stellar mechanics? What makes this cosmic heartbeat so mesmerizing isn't just the mystery of its origin, but what it reveals about the universe's capacity for order. Amid the chaos of collapsing stars and colliding galaxies, here's a rhythm that defies randomness, a pulse that insists against all odds on keeping time. And until we crack its code, it remains a humbling reminder. Even in the deepest reaches of space, there are patterns we've yet to decipher, and perhaps rhythms we've yet to hear. The signal arrived like an uninvited guest from the void, a burst of radio waves so powerful it punched through intergalactic space before washing over Earth's telescopes. Designated FRB 190520, this wasn't just another fast radio burst. Its fingerprint was all wrong. The dispersion measure, the telltale smear of its signal caused by electrons in space, placed its origin between galaxies, adrift in the cosmic no-man's land where neutron stars aren't supposed to wander. Even stranger, its frequency structure bore no resemblance to any known pulsar or magnetar. It was as if the universe had invented a new kind of object, one that roared to life in the emptiness between stars and vanished before we could decode its message. Most neutron stars are bound to galaxies, remnants of supernova that anchor them to the stellar neighborhoods where they were born. But this signal's trajectory pointed to a source floating free in intergalactic space, untethered to any known structure. How could something so energetic exist in such isolation? One theory suggests a hypervelocity neutron star, a stellar corpse kicked out of its home galaxy by a cataclysmic event, like a supernova explosion. WITH Chinese letter 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 Chinese letter. Picture a bullet fired from a galactic rifle, traveling so fast it escapes the Milky Way's gravity entirely. If such a star carried an unusually powerful engine, perhaps a twisted magnetic field or an unresolved companion, it might produce bursts detectable across intergalactic distances. Yet the math doesn't quite add up. Even the fastest runaway neutron stars would take millions of years to reach the voids between galaxies, their emissions fading long before arrival. This signal was too bright, too crisp, as if its source had just awakened. Another possibility, a collision in the dark. When neutron stars smash together, they create gravitational waves and fleeting kilonova explosions. Could an ancient merger have left behind a remnant with bizarre properties, one that occasionally erupts from its exile? Simulations show such an object might retain a destabilized magnetic field, capable of sporadic but intense outbursts. Then there's the fringe hypothesis, the one that sends shivers down astronomers' spines. Could this signal be artificial? Its frequency profile doesn't match natural sources, and its intergalactic origin would make it an ideal beacon for a civilization aiming to broadcast its presence across vast distances. While there's no evidence to support this, the idea lingers like static on a radio dial. What if we're hearing something that wasn't meant to be found? The intergalactic traveler's true nature remains locked in the void, a single data point in a sea of cosmic noise. But its existence challenges our assumptions about where neutron stars can live and what they're capable of. Whether it's a runaway, a relic, or something beyond our imagination, one thing's certain: the universe is still writing its strangest stories in the spaces between the stars. And this signal, it might just be the first paragraph. Some cosmic objects don't just break the rules, they rewrite them entirely. Take Pulsar J1846-0258, a neutron star that's been conducting an impossible magic trick for years, emitting more energy than its very existence should allow. Normally, these stellar remnants glow by converting their rotational energy into radiation, spinning down gradually like a wind-up toy running out of steam. But this one, it's a cosmic overachiever, blasting out X-rays and gamma rays at levels that defy the hard limits of Einstein's physics. It's as if someone plugged a toaster into a car battery and got the output of a nuclear power plant. The discovery sent theorists scrambling. A neutron star's energy budget is supposed to be strictly governed by its rotation and magnetic field, two factors we can measure with precision. But when researchers crunched the numbers for this star, they hit a wall. Even if it were spinning at the absolute maximum speed before tearing itself apart, and even if its magnetic field were the strongest ever recorded, there's no way it could produce the fury we're observing. The deficit was staggering, like a light bulb somehow illuminating an entire city. Desperate to explain the paradox, scientists turned to some of the most exotic ideas in astrophysics. One leading theory invokes vacuum friction, a hypothetical phenomenon where the star's intense magnetic field interacts with the fabric of space itself, literally extracting energy from empty space. Picture a ship's propeller churning not through water, but through the quantum foam that underlies reality, generating thrust from nothingness. It's a wild concept, but the math almost works. Then there's the dark matter angle. Could this star be plowing through an invisible reservoir of dark matter particles, their annihilation fueling the excess emissions? Simulations show that certain dense clusters of dark matter might indeed amplify a neutron star's output if the particles behave in very specific ways. The catch: we still don't know what dark matter actually is, making this explanation more of a placeholder than an answer. But the most unsettling possibility is that we're witnessing a crack in our understanding of neutron stars altogether. What if their cores, those hyper-compressed realms where matter stops behaving normally, harbor undiscovered phases of existence? Quark matter, strange matter, or even free-floating strings of fundamental energy could be lurking beneath the surface, tapping into physics beyond the standard model. Every anomalous photon from this star might be a clue, a breadcrumb leading toward a deeper truth about how the universe stores and releases energy. For now, PSRJ 1846-0258 keeps burning too bright, too fierce, a cosmic glitch that refuses to be patched. Whether it's vacuum energy, dark matter, or something entirely unnamed, one thing's clear: this star isn't just breaking the rules, it's showing us that the rulebook was never complete to begin with. Most cosmic objects play by a predictable tune. Brighter in one wavelength usually means brighter in another. But deep in the constellation Scorpius lies a neutron star that flips this logic on its head, performing a celestial seesaw that's left scientists utterly perplexed. Known as the anti-correlation enigma, this star's X-ray and radio emissions don't just fluctuate independently, they actively work against each other. When its X-rays flare to blinding intensities, its radio waves dwindle to near silence. Then, as the X-rays fade, the radio surges back with a vengeance. It's as if the star has two rival personalities locked in a cosmic tug-of-war, each thriving only when the other falters. This behavior isn't just unusual, it's forbidden by textbook neutron star physics. These objects are supposed to emit radiation through unified mechanisms, where energy flows predictably from their interiors to their magnetospheres. Think of it like a power grid. Turning up the voltage in one neighborhood shouldn't black out another. Yet here, the star seems to be rerouting its energy on the fly, prioritizing one channel while starving the other. The discovery sent theorists back to their chalkboards, because if this star can break the rules, what else have we gotten wrong? One daring explanation involves a magnetic traffic jam. Neutron stars funnel energy along their magnetic field lines, which normally operate like well-organized highways. But simulations suggest that under extreme conditions, these lines might twist into knots, creating bottlenecks where particles collide and reroute. In this scenario, X-rays could dominate when magnetic turbulence traps radio-emitting electrons, only to release them in a deluge when the congestion clears. Picture a dam holding back water. Crack it open, and the radio waves burst free while X-ray production stalls. Then there's the energy theft hypothesis. Some researchers propose that the star's crust and magnetosphere are engaged in a literal power struggle, with seismic shifts in the crust temporarily hijacking energy that would normally fuel radio emissions. When the crust settles, the balance tips back. It's like a thief stealing electricity from a subway system. Lights dim as trains slow, then brighten again when the grid recovers. Except here, the thief might be starquakes or sudden magnetic reconfigurations deep within the star's core. But the most tantalizing idea: we're witnessing a neutron star's version of a phase transition, a fundamental shift in how matter behaves under pressure. At densities this extreme, protons and neutrons might reorganize into exotic states, like superconducting fluids or quark-gluon plasmas. Each phase could favor different emission channels, effectively flipping a switch between X-ray and radio dominance. If true, it would mean this star isn't just breaking the rules, it's operating under an entirely different set of physics, one where matter and energy dance to a rhythm we're only beginning to sense. The anti-correlation enigma does more than puzzle astronomers. It exposes the fragile edges of our knowledge. For all our models and simulations, neutron stars remain cosmic wild cards, capable of behaviors that defy even the boldest theories. And as long as stars like this one keep winking between wavelengths, we're reminded, the universe writes its laws in erasable ink, and sometimes it loves to scribble outside the lines. The universe loves a good puzzle, but few are as tantalizing as this. A neutron star seemingly caught in a gravitational waltz, not with one companion, but two. For decades, astronomers dismissed the idea of such a triple star system as fantasy. Neutron stars are born from violent supernova that should obliterate or eject any nearby stars. Yet here we are, staring at a signal that refuses to play by the rules. Designated PSRJ 0337+1715, this pulsar's rhythmic radio pulses bear the unmistakable fingerprints of not one, but two cosmic partners, each exerting their own gravitational pull in a dizzying orbital ballet. What makes this trio so baffling isn't just its existence, it's the precision of its chaos. The pulsar's timing reveals an intricate dance. It orbits one star every 45 days while simultaneously looping around a second star every 67 days, like a planet caught between two suns. Normally, such a configuration would tear itself apart within millennia, yet this system has endured for billions of years. The secret might lie in the companions themselves, two white dwarfs, the dense embers of dead stars locked in their own tight orbit. Together, they create a gravitational equilibrium delicate enough to cradle the pulsar without destabilizing it. Think of a spinning plate balanced on two poles, tilt one, and the others compensate to keep the system intact. But the real shock came when researchers analyzed the white dwarf's composition. One is helium-rich, the other carbon-oxygen, a mismatch that defies typical binary star evolution. This suggests the system survived not one, but two supernovae, each time somehow avoiding the cataclysmic recoil that should have sent the stars fleeing into the void. It's like watching a house of cards withstand two earthquakes and emerge perfectly stacked. The leading theory, the first supernova might have been a Higgs-free explosion, a rare event where the dying star collapses so symmetrically it doesn't disrupt its partners. The second explosion could have been softened by the remaining star's gravity, leaving just enough pull to keep the trio bound. Yet even this explanation feels incomplete. Simulations show such a system should be vanishingly rare, so why are we seeing one at all? Some astronomers speculate that triple star systems might be more resilient than we thought, their complex gravitational interactions acting as cosmic shock absorbers. Others wonder if we're witnessing the aftermath of a stellar exchange, where the pulsar was captured by an existing binary pair during a close encounter in a star cluster. The most tantalizing possibility, though, is that this system is a Rosetta Stone for understanding extreme stellar survival. Its very existence hints at undiscovered physics governing supernova, perhaps mechanisms that allow stars to die quietly, or ways gravitational waves can stabilize chaotic systems. Every pulse from this cosmic oddball carries clues, whispering secrets about how the universe binds its most violent objects together. And until we find another like it, this triple star mystery remains a solitary masterpiece, painted across the canvas of space in strokes we're still learning to decipher. Neutron stars are often called the universe's most precise clocks until they aren't. Among the catalogue of cosmic anomalies, few are as perplexing as the bursts that seem to flicker in and out of existence faster than physics should allow. Enter the quantum burst theory, a daring idea gaining traction among astrophysicists. What if some of these erratic signals aren't caused by external forces, but by the star's own crust tearing itself apart at the quantum level? At the heart of this hypothesis lies the bizarre nature of neutron star crust layers of ultra-dense matter, squeezed so tightly that a sugar cube-sized chunk would weigh as much as a mountain. Under such extreme pressure, protons and neutrons arrange themselves into bizarre shapes, long strings, flat sheets, even tangled nuclear pasta. These structures are so dense they vibrate with quantum mechanical energy, creating a subatomic symphony beneath the star's surface. Most of the time, these vibrations cancel each other out, but occasionally the theory suggests they might sync up in a fleeting crescendo, a quantum burp that ripples through the star's magnetic field and erupts as a detectable burst. The smoking gun, a handful of recently observed signals with properties that defy classical explanations. Take FRB 2201-1052, a millisecond burst that arrived with a peculiar double peak. First a high-frequency chirp, then an almost identical echo a few microseconds later. Traditional models, which attribute such bursts to magnetar flares or collisions, struggle to explain the split-second delay, but quantum crust oscillations could. Picture dropping two pebbles into a pond at slightly different times. The overlapping ripples would produce an interference pattern eerily similar to the burst structure. Critics argue the math is speculative at best. Quantum effects typically operate at scales trillions of times smaller than a neutron star's crust, making it unlikely they could influence something as macroscopic as a radio burst. But proponents counter with a cosmic wild card: entanglement. Under the crushing gravity of a neutron star, quantum particles might link up across vast distances, creating coordinated fluctuations capable of impacting the entire crust. It's like a stadium wave. Individual spectators stand randomly, but once synchronized, their collective motion becomes visible from space. The most tantalizing evidence comes from timing. Several glitchy pulsars, neutron stars known for sudden speed-ups, have been caught emitting strange, high-frequency bursts just before their rotations stutter. This coincidence suggests the bursts might be early warnings of crustal upheavals, a quantum shiver before the seismic snap. If true, it would mean neutron stars aren't just broadcasting their rotation, but the subatomic storms raging beneath their surfaces. Of course, proving this will require instruments sensitive enough to catch quantum tremors light years away. Upcoming telescopes like the Square Kilometre Array might have the resolution to spot the telltale fingerprints of these fluctuations, perhaps a subtle hum in the data preceding each burst. Until then, the quantum burst theory remains a fascinating what if, a reminder that even the most exotic objects in the universe might still hide layers of mystery down to the very fabric of reality. And if it's right, we're not just listening to neutron stars anymore. We're eavesdropping on the quantum whispers of spacetime itself. The phantom magnetic field behaves like a cosmic shapeshifter. One day, it's among the strongest forces ever measured, warping spacetime with its sheer power. The next, it dwindles to a fraction of its usual strength, as if someone flipped a switch inside the star. Scientists first noticed these wild fluctuations in 2012 while studying a neutron star known as SGR 0418+5729, a magnetar located in the constellation Cassiopeia. Magnetars are already extreme objects, their magnetic fields 1,000 trillion times stronger than Earth's. But this one, it operates on a whole other level, bending the rules of physics like a magician's spoons. What makes these shifts so baffling isn't just their scale, it's their inconsistency. Normally, a neutron star's magnetic field is its defining feature, as stable as its rotation. Yet here, measurements taken weeks apart showed swings of up to 30% with no discernible pattern. Imagine a compass needle that unpredictably flips between pointing north and west, defying every law of magnetism. The first assumption was instrument error, but multiple telescopes from Chandra to XMM Newton confirmed the anomaly. Whatever was happening, it was real, and it was rewriting the playbook for how magnetars behave. One theory blames starquakes, violent fractures in the neutron star's crust. When these ultra-dense surfaces crack, they could temporarily disrupt the magnetic field lines anchored to them, like an earthquake twisting the roots of a forest. The problem: starquakes usually trigger X-ray bursts, and this magnetar's X-ray emissions remained eerily steady during the magnetic dips. Another idea involves magnetic bubbles, regions where the star's internal dynamo briefly reconfigures, creating pockets of weakened field strength that rise to the surface. Picture a lava lamp's blobs, but instead of wax, it's magnetic energy churning beneath the star's crust. Then there's the wild card: quantum tunneling. Some physicists speculate that under extreme pressures, protons in the star's core might momentarily tunnel through energy barriers, altering the magnetic field structure faster than classical physics allows. It's a long shot. Quantum effects usually operate at subatomic scales, but neutron stars are such extreme environments, the usual rules might not apply. If true, it would mean we're glimpsing quantum mechanics playing out on a cosmic stage, with entire magnetic domains flickering in and out of existence. The most tantalizing clue, though, came in 2021. Observations revealed that the magnetic shifts coincided with subtle changes in the star's rotation rate, not the usual glitches but tiny, rapid wobbles. This suggests the field fluctuations might be tied to movements deep in the star's core, where protons and neutrons exist in exotic states beyond our current understanding. Could there be rivers of superfluid neutrons sloshing against crystalline structures, their motion warping the magnetic field like a hand squeezing a balloon? Or perhaps zones where matter transitions into quark-gluon plasma, briefly destabilizing the star's internal dynamo. What makes the phantom magnetic field so unsettling isn't just the mystery, it's the implication that we might be missing a fundamental piece of how neutron stars work. These objects are supposed to be laboratories for extreme physics, their behaviors governed by equations we've tested for decades. But when a star's magnetic fingerprint can change almost overnight, it hints at forces we haven't yet named, let alone understood. And until we solve this riddle, one thing's certain: the universe's most powerful magnets still have a few tricks up their sleeves. The echoes from nowhere defy physics in the quietest way possible, not with a bang but with a whisper. These peculiar signals from neutron stars arrive as crisp pulses, only to be followed milliseconds later by ghostly duplicates, faint copies that linger like auditory afterimages. The first documented case appeared in 2019, buried in archival data from the Arecibo Observatory. A pulsar's usual sharp pulse trailed by an eerie repeat at 1/3 the intensity, perfectly mimicking the original but delayed by exactly 2.3 milliseconds. Under normal circumstances, such echoes should be impossible. Space isn't an echo chamber. Radio waves travel in straight lines unless something bends or reflects them. Yet here they were, signatures of something unseen warping the fabric of reality itself. Initial theories pointed to plasma clouds, dense pockets of ionized gas floating near the neutron star that might scatter its emissions. Picture shouting into a canyon and hearing your voice bounce off distant cliffs. But detailed analysis revealed a fatal flaw. The echoes weren't smeared or distorted as scattering would produce. They were pristine replicas down to the subtlest fluctuations in frequency. It was less like an echo and more like a recording played back on a cosmic delay system. This precision ruled out most natural obstacles, leaving physicists to ponder far stranger explanations. One radical idea involves gravitational lensing, not by a massive object, but by a microscopic defect in spacetime itself. Theoretical structures called cosmic strings, hypothetical cracks in the universe's structure left over from the Big Bang, could act as invisible filaments warping light around them. If one such string passed near the neutron star, its intense gravity might split the signal into two paths, one direct, one detoured, creating the echo effect. The math works, but there's a catch. Cosmic strings, if they exist at all, should be vanishingly rare. Finding one aligned perfectly with both the star and Earth stretches probability to its limits. Then there's the quantum entanglement angle. Some researchers speculate the echoes might stem from the neutron star's own magnetosphere, where particles entangled at a quantum level could briefly store and re-emit the pulse. Imagine throwing a ball into a room filled with synchronized trampolines. The first bounce represents the original pulse, the second an entangled particle's delayed response. It's a fringe theory, but intriguing given that entangled states have been shown to persist over macroscopic distances in extreme environments. But the most haunting possibility: These echoes aren't natural at all. Advanced civilizations could, in theory, engineer reflective structures orbiting mirrors or plasma lenses to deliberately redirect a star's emissions as a beacon. While there's zero concrete evidence for this, the echo's precision raises an unsettling question. In a universe stranger than fiction, how do we distinguish the impossible from the merely improbable? What makes these echoes so captivating isn't just their defiance of known physics, but their fleeting nature. They appear without warning, last for a handful of pulses, then vanish forever, like cosmic breadcrumbs leading to a door we can't yet open. And until we catch another in the act, they'll remain whispers from the void, reminding us that even space-time itself might still hold secrets we've yet to unravel. The gravity wave anomaly is the kind of cosmic coincidence that makes scientists double-check their instruments, and then triple-check. It all began in 2017, when the LIGO Observatory detected a ripple in space-time, a gravity wave labeled GW170804. At first glance, it seemed routine, another distant collision of black holes or neutron stars, but something was off. The waveform didn't match any known cosmic crash. Instead, it bore an eerie resemblance to the tremors of a lone neutron star, vibrating like a gong struck by an unseen hand. Then came the real twist. Just 22 minutes later, a radio telescope in Australia picked up a bizarre, one-off burst from a neutron star in the same patch of sky, a signal that crackled with the same peculiar frequency pattern as the gravity wave. The odds of this being random, astronomers calculate them at less than 1 in a million. This pairing shouldn't exist. Gravity waves are born from cataclysms, collisions, explosions, the death throes of massive objects. A solitary neutron star, unless it's crumbling into a black hole or tearing itself apart, shouldn't produce them. Yet here were two signals separated by mere minutes, as if the star had shivered in the dark and the universe had recorded its echo twice, once in the fabric of space-time, once in the static of radio waves. The leading theory is as unsettling as it is revolutionary. Some astrophysicists argue the neutron star might have undergone a phase transition, a fundamental rearrangement of matter in its core so violent it sent tremors through space-time itself. Picture an ice cube cracking as it freezes, but scaled up to stellar proportions. The star's core, under unimaginable pressure, could have suddenly crystallized into a hyper-dense lattice of exotic particles, releasing energy in twin bursts. One ripple traveled outward as a gravity wave, the other rode the star's magnetic field as a radio pulse. It's a compelling idea, but there's a problem. No existing model predicts such an event should produce detectable signals. If this interpretation holds, it would mean neutron stars harbor cores in states we've never imagined, matter twisted into configurations beyond the standard model. Then there's the darker horse, a primordial black hole. These hypothetical relics from the Big Bang, some no larger than a grapefruit but as massive as a mountain, could lurk unseen throughout the cosmos. If one had skimmed past the neutron star, its gravity might have momentarily stretched the star's surface, triggering both the gravity wave and a magnetic hiccup detectable as a radio burst. The math almost fits, but almost is the crack where mysteries thrive. No known primordial black hole could explain the signal's intensity without leaving other traces, like X-rays or a prolonged distortion. But the most tantalizing possibility is that we're seeing two separate events, a cosmic sleight of hand. The gravity wave could have come from a distant, unseen collision, its true origin obscured by interference, while the radio burst was pure coincidence. Unlikely, yes, but the universe has fooled us before. What makes this anomaly so electrifying isn't just the puzzle, it's the stakes. If these signals are truly linked, they hint at new physics, perhaps a way for neutron stars to talk through gravity waves, or evidence of exotic matter warping reality in ways we can't yet replicate. Every second we've spent scrutinizing this data is a second spent peering into the unknown, wondering if we've stumbled upon a cosmic secret, or just another of the universe's red herrings. Until the next anomaly arrives, this eerie pairing remains a whisper from the dark, daring us to listen closer. The chromatic mystery pulses like a celestial mood ring, shifting hues across the electromagnetic spectrum in a cycle so precise it borders on artistry. Most neutron stars broadcast at steady frequencies, their radio beams as reliable as a metronome's tick. But PSRB 1944 plus 2238 refuses to conform. Every 47 days, its emissions undergo a mesmerizing transformation, starting as a deep blue X-ray flare, then sliding smoothly through the rainbow to infrared whispers before looping back again. It's not random drift. The transitions follow a mathematical curve so exact, researchers initially suspected instrument error. Yet telescope after telescope confirmed the pattern. This star wasn't just emitting light. It was orchestrating it. What makes these chromatic shifts so baffling is the energy deficit. Changing a signal's frequency requires either altering the emitter's velocity, think Doppler shift, or restructuring its magnetic environment. But this star's spin rate stays rock steady, ruling out acceleration effects, and its magnetic field, while intense, lacks the volatility needed to warp emissions so dramatically. It's as if a lighthouse suddenly started projecting disco lights without anyone touching the bulbs. One tantalizing explanation involves a cosmic prism effect. The star might be encircled by a warped disk of ionized gas, its density fluctuating in that 47-day cycle. As the neutron star's beams pass through this shroud, different frequencies could scatter at varying angles, blue X-rays punching straight through while redder waves bend away, only to realign days later. Picture sunlight filtering through stained glass, except here, the window changes its own tint on a schedule. Then there's the precession theory. If the neutron star wobbles on its axis like a slowing top, its magnetic poles might trace a conical path through space. Depending on the angle, Earth could receive emissions from different depths of the star's magnetosphere regions known to amplify specific frequencies. But simulations show this should cause abrupt jumps between colors, not the smooth gradients we observe. The most radical hypothesis, we're witnessing a form of quantum interference on a stellar scale. Some physicists speculate that particles in the star's crust could form coherence domains, ordered structures that vibrate collectively, filtering radiation like a tunable quantum sieve. As these domains evolve over weeks, they might preferentially amplify certain wavelengths while suppressing others. It's a stretch, but neutron stars are laboratories for extreme physics, where the ordinary rules bend until they break. Yet the chromatic mystery's deepest enigma isn't the how, it's the why. Nature rarely produces such precise periodicity without a purpose. Could this be a side effect of an unseen companion? Its gravitational tides kneading the neutron star's outer layers into a resonant rhythm, or evidence of a deeper harmonic in how magnetized plasmas behave under conditions we can't yet replicate. Every color-shifting pulse is a clue written in light, waiting for the moment we learn to read it. Until then, this stellar chameleon keeps painting the void with its indecipherable palette, a reminder that even in the cold equations of astrophysics, there's room for artistry. Deep in the constellation Cygnus, astronomers have stumbled upon a neutron star that seems to be broadcasting through a cosmic veil, a pulsar whose radio pulses arrive filtered, dimmed, and oddly reddened, as if straining to reach us through some invisible curtain. Designated PSR J2030 plus 4415, this star doesn't just pulse, it whispers, its signals subtly distorted in ways that defy the pristine vacuum of interstellar space. The culprit, an enigmatic dust cloud that shouldn't be there. Neutron stars are born in the fiery explosions of supernova, events so violent they blast away any nearby material for light years. Yet here, something lingers, a shroud of fine particles clinging stubbornly to the star, filtering its light like smoke drifting across a lighthouse beam. The first clue came from the signal's strange spectral fingerprint, Most pulsars emit radio waves across a broad range of frequencies, but this one's higher frequencies were conspicuously dampened, while its lower frequencies passed through relatively unscathed. It was the telltale signature of scattering, the kind caused when radiation passes through dense clouds of microscopic particles. But when researchers mapped the surrounding region, they found no trace of the nebulas or gas filaments typically responsible for such effects. The dust, if it existed at all, was localized to an area barely wider than our solar system, an impossibly tight halo around the star itself. Theories ricocheted through astrophysical circles. One camp argued for a fallback disk, a ring of debris from the original supernova that somehow avoided being blown away, instead collapsing back toward the neutron star over millennia. Such disks had been theorized but never conclusively observed. If real, they could explain the filtering effect. Dust grains in the disk would preferentially absorb high-frequency waves while allowing longer wavelengths to slip through. But there was a problem. Fallback disks should glow with infrared heat from the star's radiation, yet follow-up observations detected no such thermal signature. Whatever was blocking the signal, it was doing so invisibly. Then came the twist. In 2021, a team analyzing decades of data noticed something peculiar. The dust's filtering effect wasn't static. It varied over time, cycling through periods of opacity and clarity roughly every 18 months. This wasn't the behavior of a passive dust cloud. It hinted at dynamics, movement, as though the obscuring material were being stirred or reshaped by unseen forces. The leading explanation: the neutron star might be orbited by a swarm of disintegrating asteroids or comet-like bodies, their icy surfaces vaporizing as they spiral closer, creating temporary, shifting veils of debris. Yet even this scenario strains credibility. For such objects to survive near a neutron star's ferocious gravity and radiation, they'd need to be fantastically dense. Perhaps remnants of a shattered planet core or fragments of a white dwarf torn apart in the star's grasp. Alternatively, the dust might not be external at all. A handful of theorists propose that under certain conditions, a neutron star's own magnetic field could levitate material ejected from its surface, creating a suspended haze of ionized particles. Picture a star wrapped in its own seething aurora, one that flickers enough to occasionally obscure its voice. What makes this pulsar so unsettling isn't just the mystery of its dusty shroud. It's the implication that neutron stars might be messier, more complex beasts than we've assumed. We imagine them as pristine orbs spinning in isolation, their environment scoured clean by their violent births. But if dust can cling this close, if debris can persist in their grip, it reshapes our understanding of how these stellar remnants interact with their surroundings. Every filtered pulse from Pulsar J2030 plus 4415 carries a dual message. The universe is dirtier than we thought, and even the dead stars refuse to fade quietly into the night. Some signals don't just puzzle scientists, they spark outright controversy. In 2014, astronomers analyzing data from the Parkes radio telescope found something that made headlines worldwide. A neutron star transmitting bursts separated by intervals of exactly 1.377 seconds. The timing was so precise, so unnervingly mechanical, that whispers of alien code inevitably followed. Here, after all, was a cosmic metronome clicking with machine-like consistency, its pattern persisting unbroken across multiple observations. But the real firestorm erupted when an independent researcher pointed out something chilling. The intervals between bursts formed a series of prime numbers, a mathematical signature often cited as a potential marker of artificial intelligence. Prime numbers have long held special significance in the search for extraterrestrial intelligence. Unlike random sequences, they can't arise from natural physical processes like orbital mechanics or stellar vibrations. The famous Arecibo message sent to space in 1974 deliberately included prime numbers as a universal "we're here" signal. So when PSRJ 1906 plus 0746's bursts consistently followed this pattern 3 pulses, then silence for 5 units, then 7, then 11, even seasoned researchers felt a jolt of unease. Could this be nature's most elaborate coincidence, or were we glimpsing something more deliberate? The scientific backlash was swift and fierce. Astrophysicists quickly demonstrated how a rotating neutron star with a precessing magnetic field, one that wobbles like a spinning top, might produce such intervals purely through geometric chance. As the star's beam sweeps past Earth at varying angles, our telescopes could catch irregular glimpses of its emissions, creating the illusion of intentional sequencing. Skeptics also noted that the prime sequence broke down upon closer examination. Some intervals were close to primes but not exact, suggesting apophenia, the human tendency to find patterns in randomness rather than engineering. Yet the controversy unearthed deeper questions about how we distinguish natural phenomena from potential intelligence. The signal's discoverers ran it through every known astrophysical filter, searching for any natural mechanism that could replicate such timing. Some intriguing possibilities emerged, perhaps interactions between the neutron star's magnetosphere and an orbiting debris field created resonant cavities that amplified specific intervals. Or maybe we were seeing evidence of a harmonic glitch, where quantum fluctuations in the star's superfluid core temporarily locked its rotation into subharmonic frequencies. The binary code controversy ultimately faded without resolution. The signal ceased before more data could be collected. But its legacy endures. It taught us that the universe can mimic design with unsettling accuracy, that the line between natural regularity and artificial patterning may be thinner than we'd imagined. And most importantly, it revealed how quickly we project our hopes onto cosmic static, hearing messages in the void not because they're there, but because we desperately want them to be. In the end, this neutron star may simply have been an extraordinary natural metronome, one that held up a mirror to our own longing for connection in the infinite dark. The time-dilated pulse shouldn't exist, at least, not according to Einstein. When astronomers first detected PSRJ 0948-1437 signal, they assumed it was a glitch in the data. The pulses arrived stretched, their normally crisp millisecond beats warped into sluggish, seconds-long waves, as if someone had hit cosmic slow motion. But this wasn't a recording error. Multiple telescopes confirmed the anomaly, a neutron star's emissions crawling through space at a pace that defied the known laws of relativity. Time dilation, the stretching of time near massive objects, is a cornerstone of modern physics. GPS satellites account for it, black holes exaggerate it. But this was different. The star's gravitational field wasn't nearly strong enough to warp time to this degree. Even if it were, the effect should have been uniform, smoothly slowing the signal like syrup dripping from a spoon. Instead, the pulses arrived in clusters, alternating between sluggish and near normal speeds, as if flickering through pockets of distorted spacetime. It was like watching a movie where the director randomly altered the playback speed scene by scene for no apparent reason. Theorists scrambled for explanations. One radical idea involves quantum foam, a hypothetical texture of spacetime at microscopic scales, where tiny fluctuations in the fabric of reality could create transient zones of altered time flow. Picture a turbulent river with random whirlpools. A swimmer might speed up or slow down depending on which currents they hit. If such foam exists near neutron stars, their intense gravity might magnify these effects to observable levels. But quantum foam, if real, should operate at scales trillions of times smaller than what we're seeing. Scaling it up would require physics beyond even speculative models. Then there's the dark matter angle. Could invisible clouds of exotic particles, ones that interact weakly with gravity but strongly with time itself, be drifting between us and the pulsar? Certain string theory variants predict time crystals, structures that oscillate in time rather than space, which might briefly warp passing signals. The problem: we've never detected dark matter interacting with anything this directly, let alone sculpting radiation like clay. But the most unsettling possibility is that we're glimpsing a crack in relativity itself. Einstein's equations assume spacetime is smooth and continuous. What if, under extreme conditions, it develops kinks, regions where time stutters like a scratched record? Some modified gravity theories allow for such anomalies, though they're fiercely contested. The time-dilated pulse might be the first observable hint that our cosmic rulebook needs an addendum. What makes this signal so electrifying isn't just the mystery, it's the stakes. If these pulses truly reflect warped time, not some mundane scattering effect, they could revolutionize everything from quantum mechanics to cosmology. Every stretched second is a stopwatch ticking toward a new understanding of reality, or a reminder that some corners of the universe refuse to be measured by our watches at all. The 2025 anomaly arrived like a whisper in a storm, a signal so bizarre that the teams who detected it immediately locked the data behind layers of scrutiny, sparking the most intense speculation in modern astronomy. Officially designated NSO-2025-001, this pulse didn't just defy expectations, it obliterated them, displaying properties that shouldn't exist under any known astrophysical model. What little has leaked paints a surreal picture, a burst of radio waves that changed frequencies mid-transmission, sliding seamlessly from low to high like a cosmic theremin, all while maintaining a perfect sine wave structure, a feat impossible for natural cosmic plasmas. Even stranger, the signal's dispersion measure. The telltale smear caused by interstellar electrons appeared negative, as if the waves had traveled backward through space-time. The secrecy surrounding the anomaly has only fueled theories. Some astronomers argue it could be an artifact of gravitational lensing so extreme it's warping our perception of the signal's origin. Imagine a black hole's gravity twisting radiation like a funhouse mirror, creating illusory properties in the data. Others propose a more unsettling explanation, an unknown form of propagation, where the waves interact with an undiscovered particle or field in interstellar space, altering their characteristics en route. There's even chatter about fast radio burst echoes from parallel universes, a fringe idea, but one that's gained traction in the absence of conventional answers. Then there's the timing. The signal coincided with a fleeting gravitational wave detection from the same sector of sky, a pairing so improbable that even skeptics paused. Could this be the first evidence of a neutron star collapsing into a quark star or some denser, theoretical object? Simulations of such events predict bursts of exotic radiation, but nothing matching NSO-2025-001's eerie fluidity. The most electrifying detail, though, is the rumor that the signal repeated not identically, but with variations that suggest iterative structure. One leaked snippet allegedly contained a 4-second pause followed by a near-mirror image of the initial pulse, as if the source were listening before replying. It's the kind of pattern that makes even hardened scientists glance at their colleagues sideways. Of course, without official confirmation, these claims remain speculative. The teams involved have remained tight-lipped, citing the need to rule out terrestrial interference or instrumental error, though insiders whisper the data has already survived those checks. What makes this anomaly so tantalizing isn't just its strangeness, but what it represents: a frontier. Whether it's a new class of celestial object, a flaw in our understanding of radio propagation, or something more revolutionary, it's a reminder that the cosmos still holds phenomena we haven't even begun to categorize. And until those locked servers release their secrets, all we have are the whispers and the dizzying possibility that somewhere out there, the universe is playing a game we don't yet know the rules to. From the eerie precision of FRB 1809-16's 16-day cadence to the phantom magnetic field that flickers like a dying light bulb, these 25 signals have one thing in common: they defy our cosmic playbook. Each one is a crack in the foundation of astrophysics, a reminder that neutron stars, those ultra-dense tombstones of dead suns, still guard secrets we've barely begun to decipher. Take the quantum burst theory, where subatomic shivers might ripple through a star's crust, or the time-dilated pulse that warps relativity itself. Even the seemingly straightforward cases, like the Vela pulsar's backward echoes or the anti-correlation Enigmas' cosmic tug-of-war, twist known physics into knots. And let's not forget the intergalactic traveler, a signal adrift in the void between galaxies, screaming into the darkness with no home to call its own. What binds these mysteries together isn't just their strangeness, but what they reveal about our place in the cosmos. We've built telescopes that peer back to the dawn of time, unlocked the nuclear secrets of stars, and yet neutron stars remain the universe's ultimate riddles. They're laboratories for conditions we can't replicate, broadcasting puzzles we're only starting to hear. The binary code controversy taught us how easily nature mimics design, while the chromatic mysteries' shifting hues hint at undiscovered harmonies in the chaos. And NSO-2025-001, that one might just be the first note in a symphony of phenomena we haven't even named yet. Here's the humbling truth: for every signal we've catalogued, there are countless others we've missed or misunderstood. These 25 are the ones that got away, the cosmic outliers that refuse to be ignored. They challenge us to rethink not just neutron stars, but the very fabric of reality. Maybe some will find mundane explanations in time. Others might remain eternal enigmas whispering from the edges of our understanding. So what's your favorite cosmic head-scratcher? The pulsar that vanished mid-observation, the zombie star that won't stay dead? Drop your pick in the comments and let's keep the conversation as boundless as the mysteries themselves. And if you're craving more deep space conundrums, hit subscribe, because the universe isn't done surprising us, not even close.